Welcome to the next part 2 of our beginning probability. We're going to talk now about odds. Now, odds are a little different than probability. And I actually am going to jump to the bottom of this screen to kind of show you as what we just talked about was probability. Probability compares the number of favorable outcomes to the total number of outcomes, right? That's what we just talked about in the previous video. Odds compare the number of favorable outcomes to the number of unfavorable outcomes. So instead of looking at the total number of outcomes, we're actually putting it over what's left over. We're kind of split it. So if you look at the odds against an event, and I'll tell you another way to write odds, which is tends to be how I write them. So we would do failure to success. And then the odds in favor of an event, I would write down how many are the success, right? How many are in favor of that versus how many are not favor. So then I would put the failure here. So this is what we're looking at when we talk about the difference between probability and odds. And let's just do an example so I can kind of show you through an example of what we're talking about here. Suppose you have a roulette wheel that has 38 equal sized compartments. 36 are numbered 1 through 36. Half of them are red, half of them are black. The remaining 2 compartments are green and numbered 0 and 0, 0. So just to kind of show you visually what we have here, 18 of those compartments are red. Oops, we're going to do black next. Okay, 18 are black. And then 2 compartments are green. All right, given that information, what are the odds against a ball landing on red? What that means is when I write my odds, which like I said, I like to write it this way, what goes here then would be anything that is not a red, because that's our keyword right there, against. So how many of these compartments are not red? Well, that would be the 18 black and the 2 green. That's 20 of them. Then on the right, I put how many are red. That would be 18 of these. Now you can treat this still like you do a fraction, which means I can still reduce this ratio. So if I reduce this ratio, I would just divide both of those by 2, and that would give me 10 to 9. My odds then would be, and that's how we would say it, the odds against a ball landing on red would be 10 to 9. All right, let's try another example. Oops, let me just erase all that from before. All right, so another example. If 2% of the U.S. population is born with an IQ of 130 or above, which is called gifted, find the odds against an individual being born gifted. Now look at this one. You're given 2% of the population. That's the information we're given right here. Guess what that is? That is our probability. All right? So our probability is 2%. Another way you could look at that is 0.02. Or remember, let's go back to when we talked about in a very previous video, back in the finance, how to write a percent as a fraction. Remember, it's always out of 100. So 2 out of 100. This means, and I'm doing this for a reason, so the probability is 2 people out of 100 total. Then how many, that means 2 people would be gifted out of 100. How many are not gifted then? Well, that would be 100 minus 2, which is 98. So we have 98 that are not. Why am I doing this? Because remember, odds is not out of the total. You are splitting the total. So now I have my 2 right here. That's for gifted. And 98, which is the non-gifted. So when we're looking at the odds against an individual being born gifted, that means I put how many are not gifted then first. So that would be the 98 to the how many are gifted. So 98 to 2. And those are both even. They can both be divided by 2. So that would give me 49 to 1. The odds against an individual being born gifted is 49 to 1. So you're not always going to be given the 2 numbers you need, but if you know the probability, we just split that. So we split that 100 into the 2 and into the 98, and now we have our split total. You can always check. If I add these two up, the 98 plus the 2, I get back to my total, which was the probability. Next, a die is rolled. What are the odds against rolling a 3? So remember, with a die, you have the numbers 1, 2, 3, 4, 5, and 6. So it's a 6-sided die. What are the odds against rolling a 3? So against a 3. That means we're looking at how many are not a 3. Well, that's going to be 1, 2, 4, 5, and 6. That's 5 numbers. How many are a 3? Just 1. So your odds are 5 to 1. But how many odds are, what are the odds in favor of rolling a number greater than 1? So favor of greater than 1. So I'll put in favor of greater. Okay, so you want to roll a die. And what are the odds that it's going to be in favor of greater than 1? Well, how many numbers are greater than 1? Well, it'd be 2 to 6. There are 5 numbers. How many are not greater than 1? Well, that would just be the number 1. So here, notice we just got the same odds. So the odds against a 3 are 5 to 1, and the odds in favor of greater than 1 is 5 to 1. So you have the same odds for both of those. Now let's talk about finding probability from odds. So when you're looking at probability from odds, you're going to take, and we just I showed you a little example, kind of a teaser, I guess, was that example that we did. But you have the number given in the odds statement. And then remember, this is the sum of the numbers. Okay, right? Probability is always out of the total. Odds, you split the total. So let's do an example to help you kind of make sense of what I just said. Sometimes it's easier to understand when you see something. All right, we know that the odds against an event are 9 to 2. Then what would be the probability against the event? We have 9 to 2. That means the total is 9 plus 2, which is 11. So that's my total. So the probability against the event would be 9 out of the total, which is 11. Okay, so see the difference? Odds, you split the total. Probability, the total goes in the denominator. Here it says, what's the probability then in favor of the event? Well, if the odds against was 9 to 2, then in favor it would have been the 2. And then it will be out of 11. That's how you can find probability. So if you know the probability, you can find the odds. If you know the odds, you can find the probability. Next example, if the probability of an event is 0.65, what are the odds against the event? All right, probability is 0.65. As a fraction, remember that would be 65 out of 100. Well, then that means I can split this up. What is 100 take away 65? 35. Okay, let me just kind of underline. So notice this, we just split the total. We just split the total of the probability, and now we have the two numbers that we need. So here, we want the odds now against the event. Well, the probability for the event was 65. So the odds against the event would be the 35. So it'd be 35 to 65. And again, that total does come out to be 100, so we know we split it fine. So that would be when you find the probability, split up the total, and then you can use those two numbers for your odds. Now, let's talk about a tree diagram. A tree diagram is when you're literally drawing a diagram, and it has branches, hence why it's called a tree diagram. And you're going to see, I'm going to do an example here. In fact, I'm going to need a lot more space than that to draw this. We're going to toss 3 coins. Now, each coin, right, has 2 options, heads or tails. We want to determine the number of sample points in the sample space. I'm actually going to first do that by constructing a tree diagram. How do we do that? We're tossing 3 coins. Now, when you toss the first coin, what are your options? You could get a heads, right? Or you could have a tails. That is your option with coin 1. But now I'm going to toss a second coin. What are options with the second coin? A heads or a tails. But now, let's say the first coin landed on heads. Well, with the second coin, I have the option of a heads or tails. Let's say the first coin landed on tails. Well, again, with the second coin, I have the option of a heads or a tails. But now we have the third coin. With the third coin, you still have the option of heads or tails, but notice all of these possible outcomes that already could have occurred. That means with each of these possible outcomes, I could have a heads or a tail with the third coin. Okay, so this is coin 1 in the blue, coin 2 with the red, coin 3 in the green. All together, how many outcomes do you have? What you do is you look at the very last, oops, made a mistake there. You look at the very last branches. However many branches you have, that's how many outcomes you have. 1, 2, 3, 4, 5, 6, 7, 8. So the number of sample points, and we're going to write them out in a minute, would be 8, meaning there's 8 possible outcomes. What are those outcomes? I do want to kind of show you real quick. Here you're looking at all 3 coins could have been heads, right? Heads, heads, heads. You follow the branch. So here's one possible outcome is that every coin gave you a heads. Or you could have had a heads with the first coin, heads with the second coin, but a tails with the third coin. So there's another outcome. Look over here. Now we could have gotten a heads, a tails, and a head. Or a heads, a tails, and a tails. Notice these are showing you the branches, kind of show you your possible outcomes. Here we could have gotten a tails, heads, heads. Tails, heads, tails. I'm going to speed things up a little bit here. Heads, tails, tails, heads. Or all tails would be the last branch. These are your 8 possible outcomes you could get with coins 1, coin 2, and coin 3. Given that information, what is the probability that at least one tail is tossed? At least one tail. Well, we know altogether we have 8 possible outcomes, right? Remember, probability always out of the total. How many of these outcomes do you see where there's at least a tail in there? Well, it would be every single one except the first one. So 7 of those outcomes has a tail. Then it says, what is the probability that all 3 heads are tossed? Still out of 8, but how many of those outcomes do you see where it's all 3 heads? Just one outcome, one of those. 1 out of 8 would be my probability then. Now let's jump to something called the fundamental counting principle. This is actually kind of easy. I like this one. It's called the multiplication principle for counting outcomes. So suppose there are m, whatever that number is, so it's just a number. There's m possible outcomes for one process and n possible outcomes for a second process. The total number of possible outcomes then is going to be m times n. Let's go back here. Let me just kind of show you here. Look at this. In this problem here, we were tossing, right? We were tossing 3 coins. You had, 3 coins. How many outcomes did you have for the first one? Well, 2, heads or tails. For the second coin, same, heads or tails. And for the third coin, you had 2 possible outcomes. To figure out how many outcomes altogether you're going to have, you just multiply that. And so 2 times 2 times 2 is 8. And then we could find with the tree diagram what those actual 8 outcomes would be. So that is the fundamental counting principle. So let me just show you an example here. How many possible outcomes can be obtained when a fair coin is tossed once and a fair die is rolled once. We have two events. We're doing a coin and we're rolling a die. How many possible outcomes do you have with a coin? We just talked about that. Two outcomes, heads or tails. How many outcomes do you have when you're rolling a die? 6. Remember, the number's 1 to 6. 6 possibilities. Multiply that together, and you have 12 possible outcomes. And you can list that out, right? You could have a heads and a 1, a tails and a 1, heads and a 2, a tails and a 2, and so forth. And you're going to have 12 of those. But that's what the fundamental counting principle is. Look at this one. Tony has 7 shirts, 3 sweaters, and 4 pairs of pants. How many possible outfits does he have? So look at that. Out of 7 shirts, we're going to multiply that by 3 sweaters and multiply that by the 4 pairs of pants. That's what the fundamental counting principle says. You multiply all of your possible outcomes. So in this case, we would get 84 possible outfits. Who knew with just that little bit how many outfits you could have? Now, number 3, if you are tossing 4 coins, how many ways could that be done? In other words, how many possible outcomes are there? Well, again, we have 4 coins, and I know I multiply. 2 outcomes for each coin. So we're multiplying, basically that's, in a way, I'm just going to show you, that's 2 to the 4th. You don't have to do that, but it's 2 to the 4th. But that would give us 16 possible outcomes that you would be finding when you are looking at that. Number 4, in a certain state, license plates consist of 2 letters followed by 3 digits. How many license plates are possible? Now, we're going to assume repetition is allowed, and then we'll assume repetition is not allowed, and I'll explain what that means. First, let me make my little dashes. This is just how I do it. I have 2 numbers followed by 3 digits. So I'm going to make sure I have my slots ready to go. How many letters are in the alphabet? 26. So I have 26 possibilities in each of these 2. How many digits are there? Now, when we're talking about digits, let me just kind of put it over here. We're talking about single digits. So that would be the numbers 0 to 9. It's always going to be that. So we're talking about digits. We mean 0 to 9, which means there's 10 digits total. So I have 10 possibilities in each slot. Now on your calculator, you're going to multiply that all together. Okay? So if you multiply, meaning you're going to take the 10 times 10 times 10, right? And then the 26 times the 26. What we get is 276, sorry, not 200. Let me erase that. I don't know why I said 2. That's not what I see on my calculator either. 676,000. So that's how many outcomes you have when repetition is allowed. What does that mean? That means that if you had an A, you could have an A again. There's no rules about that. But now look at this one. Now let's assume repetition is not allowed. Same dashes because we still have 2 letters followed by 3 digits. 26 letters to choose from, but here's the key. I'm putting up here. Repetition is not allowed. That means that whatever letter gets chosen here cannot be chosen here. That means that I only have 25 letters to choose from now. That's the difference. When repetition is allowed, you can keep repeating it. When repetition is not allowed, you're going to lose a number each time or letter. Same thing with the digits. I have 10 digits here to choose from, but now I can't use whatever digits there. That means I have 9 to choose from in this slot. But now I can't use that one, so I have 8 to choose from there. That's going to change your numbers, and actually it will give you less when you have that rule. And now we have 468,000 possibilities. So when repetition is allowed, you do lose a good amount of outcomes, possible outcomes. All right, one last one. If a club has 20 members, in how many ways can they elect a president, a vice president, and a treasurer, and assuming that no person can be selected twice. Okay, so president, vice president. So you have 20 people to choose from, but you can't choose the same person, right? Whoever got chosen for president can't be here now. That means I have 19 left to choose from for vice president, and then 18 left to choose from for treasurer. That gives me 6,840 possible outcomes or possible combinations. All right, I'm going to end here, and then in the next video, part 3, we will start talking about relative frequency.